I'm Sarah Beery. I'm a new assistant professor at MIT, and I'm also a PI at the Computer Science and AI Laboratory. And my new research group is really focused at this intersection between AI, biodiversity, and ecology. We're interested in developing AI techniques that help us better understand how species are changing at a global scale. And we do this across different data modalities, everything from images to acoustics to sonar to remote sensing data. And we combine these different modalities and try to interpret them so that we can understand how species are changing at a global scale. So actually, I've always loved the natural world. I grew up camping with my family in the Pacific Northwest, but actually my first passion was dance. I started training as a ballerina very seriously. I got my first job offer with the Atlanta Ballet when I was only 16, and I moved from Seattle to Atlanta by myself to join a ballet company. I lived in sort of like a not super great area that was kind of close to Georgia Tech. They would put posters on the telephone poles for scientific talk that always advertised free food. So I would go. I almost immediately found myself hooked on the science. And not specifically science writ large, but it was eye-opening to me in terms of how science and technology can be used as a force for public good. And that planted this seed. So I went on and I continued to do professional ballet for 6 years. I loved it. But I started to think about how I might instead go back after I retired from ballet and become a scientist. And I ended up doing that. I went back, I retired from ballet, and I started a career in electrical engineering. So one of the projects I actually started in my PhD and have brought to my lab here at MIT is a project looking at improving the sustainability of the salmon fisheries from Alaska all the way down through Canada to Northern California.
This project is working with stakeholders in fishery management and conservation who are interested in monitoring the number of salmon migrating every year. And to do this, they deploy sonar video cameras at rivers around the world, and they have technicians deployed there throughout the migration season counting how many salmon are moving by the cameras every day. We're working on developing computer vision algorithms to make the process more efficient and more accurate for them. So most of these sonar camera deployments are out in the field with limited connectivity and power. A solution that we've been working on for deploying these algorithms uses edge computing. It's basically a low-power, low-cost Linux computer that can be deployed out in the field and powered by solar. And we can deploy the model on this device. And we have a software application that runs that allows technicians to analyze all of their video. The way that the algorithm works is that each individual fish has a different colored box drawn around it. It has a length estimation. And then at the bottom, we say how many fish have gone left or right. And they, based on the orientation of the camera, then change this to upstream or downstream counts.
So our interests are really, from a research perspective, how do you effectively use human time, human decisions throughout this process so that you can maintain the reliability of the system, but also make it reasonably deployable. The next project I want to talk about is a little more open-ended. And here, what we're interested in is as we start collecting these large repositories of data from different data modalities, like the fish sonar, but actually specifically in this project, data collected from passionate volunteers around the world who will take photos of plants and animals that then become species occurrence records. And the way that they do that, one mechanism they do that, is through a platform called iNaturalist.
We're using embedding models, which are AI models that are trained to find the semantic relationships between images and text. So we're able to pre-compute these sort of semantically meaningful embeddings on all of our 5 million images. So when you're trying to search through and you give us a piece of text describing what you're looking for, we can, in less than a second, look through and compare with all the millions of images we have to give you exactly the closest match for what you're looking for. We hope that our data set will provide the foundation and the motivation for researchers in the field to actually work on building models that are not just generally good, but actually useful for scientists. One great example is California condors. This is a species that almost went extinct in 1982. There were only 22 individuals left. But because of a successful breeding program, now there's a stable population of hundreds. And scientists still want to track them to monitor the population and understand where they are and what they're doing. So all California condors have tags on them with a color and a few symbols that identify who they are. And so scientists can't be everywhere all at once, so it's been really difficult to be able to successfully monitor them and see where they're going. But now with citizen science and regular people taking pictures of these birds they find interesting and uploading them with geotagged locations, we can automatically mine this information with these vision language models that understand both text and images to pinpoint all of their locations and track them in a way that we've never been able to do before.
So that we can try to design systems that enable lots of scientists to do diverse science efficiently, and hopefully opening up whole new avenues for scientific discovery. When I was in grad school, I was passionately working on developing these tools for ecologists in the field, but I realized I hadn't had that experience of actually trying to collect data and deploy monitoring systems in the field myself. So I went out of my way towards the end of my PhD to actually start curating some of that experience. I really found it invaluable. My first version of this, I planned a survey using static cameras in Laikipia County in Kenya, sort of north of Mount Kenya, where we were trying to study an endangered species of Grevy's zebra. And I went out and I placed all of those cameras myself, hiking out sometimes miles into the forest with a ranger with a gun, because you're dealing with very dangerous large species out in the savannah, and really understanding how much time and effort goes into collecting every single data point. It really gives you a different mentality about how to value that data. But not only that, there are things that you don't even realize are challenges if you're just sitting behind your computer writing code, that actually really reframe the priorities I think I have in my research. I found that experience incredibly rewarding, but also incredibly informative. And it's now something I really seek to continue to do in my lab here. I want to require all of my grad students to go to the field, to be working much more hands-on with specific projects. Maybe not for every project, but I think it's really valuable context. And it does actually mean that often our group and my own research, we've brought new challenges to the machine learning community, framed problems in ways that potentially they hadn't before seen them. And I think it's really that application-driven innovation that really helps us move the needle in terms of what machine learning needs to do. One of the things I'm really excited about moving forward is actually starting to bridge the gaps between these different data modalities that are being collected globally, combining these hyperspectral imaging systems from space with drones capturing individual animals moving through the environment, with static networks of bioacoustic sensors, photos collected by passionate human volunteers, actually sharing information across these modalities of data so that we can get a much more nuanced picture of the tree of life. I think if I had any advice for anyone who's excited to get started in this field, it would be to just talk to people. And there's increasingly these amazing communities, resources that are coming together. I run a Slack channel that has 2,500 global researchers on it, just working on AI for conservation. Getting onto these platforms, meeting people, asking questions, putting yourself out there, but learning about sort of all of the different diverse ways that people are sort of tackling these problems. I would love to see this continue to grow.